Hey students, we're going to cover the universe today, but before we do that, I want to review the standard particle model. What that is it's a collection of all the basic particles we know about, which get assembled in different combinations into stuff like atoms and other things. What you're looking at right here is one pretty cool experiment that starts out with a particle accelerator, gets things going really, really fast, smashes into a target. All of the kinetic energy in the high-speed particle is going a fraction of the speed of light, like crazy fast. It'll convert into other stuff, and you can do some nuclear reactions with that. So what they're getting out of this is a thing called a neutrino. They don't interact with stuff. So what's weird is they can go through the entire Earth and not hit anything. You guys know X-rays can go through you, right? Well, this is a particle that just doesn't interact with stuff. It almost never does anything. And so it can go through 800 miles of rock, and it'll go right through the detector too, to be honest, most of the time. But occasionally it does interact with something in the detector, not very often, and they'll get a hit, and it'll make a flash of light that these super sensitive photomultiplier tubes will pick up when this thing is filled with water. Things buried underground so that only neutrinos are interacting with stuff in there. It's kind of crazy. So here's another really cool one. This is a picture of a detector in CERN, the world's biggest super collider. With this thing, they can dump in so much energy into lead ions that when they smash them together, they can make all kinds of crazy stuff. This experiment can make the highest energy level, highest temperature, highest pressure regions on a microscale, and you can get all kinds of exotic particles to come out. Now, what would be normal would be exotic. You guys remember electrons, protons, and neutrons are part of the atom. And while electrons, as far as we know, are a fundamental particle, protons and neutrons are made of smaller pieces called quarks, set up in sets of three. So two up quarks and a down quark makes a proton. One up quark and two down quarks makes a neutron. Again, protons and neutrons are these basic first generation particles in sets of three. The second and third generation particles are like the first generation in a lot of their properties, but have a much higher mass and tend not to be as stable. But you can definitely build those things using E equals mc squared, energy to matter conversion, in one of these particle supercolliders. One other thing you might remember is that gluons are the force mediating particle for the strong nuclear force, the thing holding the quarks together. Gluons do not affect electrons, which is why you get electrons outside the atom in an electron cloud. Whereas electrons and protons both, they have charge, so they can both be influenced by photons, which mediates electromagnetic force. Last up, we don't know as much about gravity as we'd like to. We know that something about mass and inertia comes from the Higgs field and Higgs boson. We haven't actually identified individual gravitons as a particle on this chart. So you'll notice that gravity is missing from this model. That is still something that needs to be researched and developed. The rest of this model is working very well in all the experiments they're doing, ones like this in a super collider experiment. So again, that's CERN. By the way, there's a Google Expeditions. If you guys have Google Cardboard or like a 3D VR viewer, you can go check that out. It's pretty cool. Normally we do that in class. All right, what else can you do besides sets of three? You can also put together quarks in sets of two. You can have an up quark and a down quark. You can have an up quark and an anti-up quark. Or a down quark and an anti-down quark. So sets of two is a possible arrangement. Under extremely high temperature, energy, and pressure, you can also get individual quarks, not bonds to other quarks, but that would be like under crazy conditions. So all of this depends on what's the average energy and pressure level there. Under normal circumstances, like we think of today, sets of three is the norm. Under high energy, high pressure, high temperature, you could get sets of two as the norm. And under extreme conditions, you could even get individual quarks. So let's keep going. We're going to cover the universe, kind of its history and hierarchy. You guys are going to know what we can observe about it and what that tells us about its past. You guys are going to know why we know there's a Big Bang. You're going to be able to also look at kind of just more general information on galaxies and solar systems, which are both on a much, much, much smaller scale. We're going to look at how much smaller. And if we have time, we'll get into some features of our own solar system. So here's some cool vocab. You guys can pause it and take a bit of a look here if you want to. We'll try to cover most of the stuff in blue today if we can. I doubt we'll get that far, but we'll see. And let's start out right here with, what do we mean when we say the universe? We mean everything that we can observe. So if it's observable, it's part of the universe. As far as science is concerned, the universe is everything that we know about and everything that we can measure. We can't observe outside the universe. Then it would still be part of the universe. So this is as far as we can see, basically, as far as we can measure or determine anything about it. So when we say the universe, we basically mean everything. It's the biggest thing on this list. Okay, within the universe, you get all kinds of clumping up of stuff on all kinds of different scales. So the rest of this is clumped up because of gravity for the most part. So you can say a supercluster is when you have many, many galaxies in a small group, kind of, sort of held together by gravity a little bit. A galaxy is like a million stars, pretty well held together by gravity. They tend to orbit and rotate in the same way that we'll have planets going around the sun, but in this case, it's stars going around the galactic core, which is also made of stars, possibly a black hole too. Okay, star clusters would be within a galaxy, just like 100 stars or 1,000 stars that came out of kind of a similar size nebula. And then individual stars, or sometimes they come in pairs, or very rarely in trios. So binary star systems are not super uncommon. You might get a bunch of like junk floating around the star, and that's the stuff we call planets, asteroid belts, comets, Kuiper belts, etc. So when we say solar system, that's actually at the very smallest level. When you guys think of the sun as big, on the scale that we're talking today, it's really not. It's really about the smallest thing we're going to pay attention to. So with that, let's watch a cool video here. It's based on powers of 10. We're going to start with the smallest thing, and we're going to zoom our way out to the biggest thing. So we're going to start with quarks, the smallest thing that we know about. Each circle represents 10 times bigger. Now you're looking at neutrons and protons in the nucleus of an atom. Now you're looking at the electron cloud. Multiple atoms bonded together can make, oh, there we go. We got the full atom now. So now we're outside the electron cloud, and the atoms are bonded together into molecules, which are still much smaller than even the smallest thing. So now you might be like right around the size of a virus, or like a protein. Now we're looking at cells. Remember, each time it zooms out is 10 times bigger. Okay, an interesting thing to know about. One type of distance we talked about is, I'm going to mute it for a sec here. Sorry, hopefully you guys can still hear. So one type of distance we talked about is AU, astronomical units. It's the average distance from the Earth to the Sun. So AU is Earth to Sun, counts as 1. Another way to think about that is that it takes 8 minutes for light to travel from the Earth to the Sun. So 8 light minutes is 1 AU. I'm actually going to pause here for a sec. Let's get this idea down. So if something happened on the sun, you wouldn't see that until the light arrived at Earth, and it would take 8 minutes traveling at the speed of light to get there. That's what 8 light minutes means. The moon, which is the farthest a person has ever traveled, is 1 light second. So that's why they're like, Houston, we have a problem. 1, 2. Oh, what's your problem? 1, 2. Our spaceship blew up. 1, 2. That's really bad. I hope you guys don't all die. 1, 2. Yeah, let's put these round filters in square holes. 1, 2. Okay, let's get the duct tape. 1, 2. So if you guys hear the old videos from the moon missions, there's a transmission delay. And that's because of the time it takes for light to travel across pretty big distances. Again, Earth to moon is 1 light second. Earth to sun is 8 light minutes. To the nearest star, we're looking at 4 light years. So like if something happens on Alpha Centauri, it takes 4 years for us to notice it. Or if we're looking through our telescope right now at Alpha Centauri, what's really cool is that that light is 4 years old. You're looking 4 years into the past when you look through your telescope at Alpha Centauri because of the time it takes for the light to transit. So that's kind of amazing. The farther away you look with the telescope, the more into the past you're looking. So keep that in mind here, and we'll keep going. Okay, so what's the thing you're looking at in terms of that scale? That is a galaxy. We're now halfway up that kind of hierarchy chart. What is holding that galaxy group together? It is gravity. All of the clumping you're seeing is based on gravity. Alrighty, there we go. Got about 100 billion galaxies. And let's see, where is our marker of how far zoomed out we are? I don't know. Alrighty, well, there we go. So when we say universe, it is ginormous compared to other stuff here. A universe counts as everything. Within that, there are clusters and clumps of different sizes. We consider even our star to be pretty big, but in the grand scheme of things, it's not. So yeah, let's keep going with that. All right. So we mentioned that looking across a large distance is actually looking into the past because of the time it takes light to travel. So one question is, how far away can we see with the telescope? And the Hubble telescope is one of our best ones. It's in orbit, so it doesn't have to look through the atmosphere. That'll kind of muck up the picture. It can also stay aimed at a certain spot. Like you guys know, camera goes click, like the old-fashioned cameras. It would only expose the film for a very, very short time, a fraction of a second. I've done some astronomy where I've had the camera open with a like a high ISO film for 5 or 10 or 20 minutes. And my dad's done some exposures at even like a 2 hour level. And the reason you're doing that is it takes time to collect light from objects that are so far away, it makes them appear fainter. Like you guys know, flashlight right in your eye, super bright. As you move it away, it looks dimmer and dimmer. So if you're looking across across the universe as far away as you can, first of all, you need a large aperture telescope, like a big amount of surface area to collect light with. So giant lenses, that gets expensive. You're going to put it in space so there's no atmosphere. You want to aim it at a dark part of the sky where there's not any bright objects in the foreground. And then you want to just keep it aimed there for like weeks or months. And so the Hubble Deep Field and Hubble Ultra Deep Field are some of the photographs in the visible spectrum that we've done this with, aimed at a dark part of the sky, looked as far away as we can, and kept it there. And what we got were these amazing photos. This is from roughly 13 billion light years away, which means that the light has been traveling for 13 billion years. So this is an image far, far, far into the past. This is actually from the very early universe, not too long after clumping actually started to get stars going and clump them into small early galaxies. So each of these things in the picture, by the way, is also a galaxy, not a star. This is already millions of stars or thousands of stars, however big these galaxies are. So this is a picture of many, many galaxies spaced out relatively close together from 13 billion years ago, just because of the vast distance we looked across. I hope that concept makes sense. Now, why can't we see farther away than this? The answer is there's not visible light coming from farther away from this. So this is about as far as you can see anything. After that, it's dark. So that's kind of cool. And we'll get more into why that is later. That's really weird. Hopefully you're starting to think about that. Now, before we get too much farther, I also want you guys to understand this concept of a standard candle. If there's a flashlight and you put it right in your eye at a known distance and it's like way bright, and then you double that distance, it should only be a quarter as bright seeming. And you double that distance again, it'll be a quarter again as bright, or 1/16 as bright as it originally is. So we know how things spread out. It's this inverse squared law you guys have already seen applied to gravity and Coulomb's law, electrostatics. So things spreading out goes at an inverse squared rate. And that has to do with the brightness of light too. So what's cool is if there's an object that you know how bright it should be, and that's what a standard candle means in astronomy, an object whose brightness is known, and you see it a certain amount dimmer than you expected it, you also can do some math and figure out how many times farther it is than the one you had previously observed. And so one thing you can do with this is Cepheid variable stars. These are stars that are extremely consistent in brightness. And the problem with these things is they're not super bright. You can't observe them from like hecka far away. You can only observe those maybe within a galaxy or nearby galaxies. If you want something super bright, you're going to have to go bigger. And for that, we want a type 1a supernova. Now, the way this works is in a binary star system, two stars orbiting at the center, not just one, kind of like Tatooine on Star Wars. You're going to have one of them be a neutron star, which is kind of the dead core left over from a prior supernova. And the second one can be gradually losing gas getting pulled off by the neutron star. So basically, the one star is feeding the other. When the neutron star gets to a critical mass, it explodes. And what's cool about this is that critical mass is very consistent. It's always the same mass when it explodes and causes a supernova of the same brightness each time. So if you see a type 1a supernova, and you see another type 1a supernova, and you can compare the brightnesses of them, you can also figure out the relative and absolute distances of them. So a standard candle is an object of known brightness that by figuring out how much dimmer it looks, we can then do math and figure out the distance of where the object was located compared to us. So this is our main way of understanding distances across outer space. Hopefully that idea just makes sense to you. Like, take a flashlight. Oh, if it's this bright here, it'll only be a quarter as bright here, and so forth and so forth. You can kind of do that math progression. As the object looks dimmer, you know that it's farther away, assuming you knew what the brightness was to start with. All right, so with that, let's keep going. We're going to kick it back to waves for a second. There's a reason we did this in order. This is an old classic. Here we go.
Edwin Hubble stated his many years of observation as a law. This was that the velocity with which galaxies move away from us is directly proportional to their distance from us. And so a graph plotting velocity against distance is a straight line. The velocity of galaxies was calculated from the redshift. One way of explaining this shift towards the red end of the spectrum is by the Doppler effect. The light is stretched out as the galaxy moves away. This is the same effect as the change in note of a passing car.
Okay, now a couple things. You guys heard the Doppler shift with that car. When it was coming towards you, frequencies were higher. When it was going away from you, frequencies were lower. Opposite statement true for the wavelengths, right? Did you see the car change color? The answer is definitely going to be no, because the car is going so slow compared to the speed of light being much faster than the speed of sound, that you're not going to notice a perceptible difference in the color of the car. However, if you had like a radar gun, that would be the kind of technology you need to notice that difference. So it's just going to use radio waves, and it is going to measure Doppler shift to be able to determine the speed of the car. So you can see red shift or blue shift. Blue would be when it's coming towards you. Red is when it's coming away from you, even with slow-scale objects with the right technology on Earth. And the good news is, in space, we're not talking about these slow, pedantic speeds. Things are going crazy fast in outer space. And there, the red shift and blue shift is actually much more noticeable. You can even measure that with just an average spectrometer. Good spectrometer can get you incredibly good data on relative velocities.
As it passes, the note becomes deeper as the waves are stretched out. There is, however, a more subtle and more satisfactory explanation. Imagine a universe like a...
All right, hold up on this. Let's go back to this graph now. So hopefully at this point you understand that these distances are determined using the standard candle method. Hubble's data was originally on Cepheid variables for nearby galaxies. We now use type 1a supernovas and a bunch of other things to get additional data on the distance axes. This is all standard candle data. You can tell how far it is because of how bright objects of known brightness are. The velocity is being determined using Doppler shift. So on this axis, we're determining how fast it's going based on light coming from it. And they're going to typically use one band in the hydrogen spectrum as the easiest reference point. It can even be emitted by low temperature, fairly cold objects like gas clouds. I think it's in the radio frequency band. So basically, like looking for, let's say something always makes a 700 nanometer light band in hydrogen, and almost everything in the universe has some hydrogen in it. So you should be able to see that particular line of hydrogen coming from any object. And then if it's not at 700 nanometers wavelength, if instead it's at like 710 nanometers wavelength, you can tell that it's been Doppler shifted by 10 nanometers towards red. And then you can tell, okay, well, red shift means it's going away from us at a certain velocity. And you can do some math, which I think I showed you guys a couple weeks ago on how fast it's actually going. Now, here's a weird thing about this graph. I want you guys to think quadrants for a second. So we got quadrant 1, quadrant 2, quadrant 3, quadrant 4. All of Hubble's data is showing up in quadrant 1. Well, why is that? Well, we're not going to think of something as negative displacement. We're only covering distances. Okay, so it makes sense that we're covering the right-hand side, quadrants 1 and 4. But what's weird is, except for galaxies that are gravitationally bound in our local galaxy cluster, which are right around the origin here, both in terms of distance and velocity, and occasionally we get like a slightly negative velocity, but it's also basically effectively at 0, 0. All the farther out galaxies are traveling away from us at increasing speeds. So one thing to think about is, for this galaxy right here, by the way, each dot represents a galaxy, not a star. For this galaxy here, it's traveling away from us, and it's not very far from us. This galaxy here is traveling away from us faster, and it's farther. Now, one question is, okay, so all these galaxies are getting farther away from the Milky Way. Are they also getting farther away from each other? And the answer is yeah, because its velocity is higher than this one's velocity, they're also separating from each other. Let's jump back to this next high expense demo.
And more satisfactory explanation. Imagine a universe like a balloon, with galaxies not only spread around the surface, but through the center as well. This model is a snapshot of an early universe that has only expanded a small amount since the Big Bang. Between the galaxies, energy passes in the form of waves. Now, if we move on through time, the universe expands. The galaxies themselves don't expand. They are held together by gravitational attraction. But the space between the galaxies expands, and with them, the waves which are traveling between the galaxies are stretched out. It follows then that the change in the wave...
Okay, so there are some weird subtleties to this. One time I was at a conference hanging out with my choice of different kinds of physicists, like everybody was grouped up in the topic tables. I chose to go hang out with the cosmologists and the astrophysics people. And I was talking about, how do you guys explain this? So I was talking about how when objects are moving away from each other, it just redshifts the light because of the relative velocities of the objects. And they actually got kind of upset over this. Apparently that's a way to trigger astrophysicists. They do not think about this galaxy and this galaxy as moving away from each other at a certain velocity. They think about space-time expanding between them. So they're actually thinking about space expanding, the galaxies being kind of dots marked within that space, and the space between them getting bigger. And the wave is also expanding with the space-time. So they're thinking of redshift as an indicator for space expansion, not necessarily as relative velocities between galaxies. And I guess at the end of the day, the math comes out the same either way you think about it. But that was an interesting difference in perspective, changed my thoughts about this quite a bit. So it's really cool if you think about this as the space between the dots expands, including stretching out the wave that's traveling through there, as opposed to like more classic way of thinking about like sound-based Doppler shifting, where it's just the velocities of object happen to be, relative motion causing those wavelengths to increase.
The wavelength of the waves is directly proportional to the amount that the universe has expanded.
All right, so we're just going to summarize real quick here. So the distances were measured using standard candle method. The velocities were measured using redshift or blue shift, although there really wasn't any. It's all redshifting. These are different galaxies being plotted. And Hubble got a Nobel Prize for putting this data on a graph, plopping a trend line down there, and then solving for the slope. That slope is now called Hubble's constant. It's the rate of expansion of the universe. By the way, if the universe is expanding moving forward, what does this all look like played back in time? Answer is it looks like contracting down from a point source. So we also have a point source idea, a concept for the start of the universe here, partly because of this amazing work. A bunch of other evidence too.
Pretty simple.
All right, let's keep going. Let me make sure that's done. Yeah, I think we're good. Okay, so audio should be working. So how else do we know? We know that the universe is expanding right now. We can see that from redshift from all kinds of different galaxies. We can see back in time what the universe looked like by looking across large distances and having that light be very old. We can also recreate early universe scenarios using those super colliders we started out the lesson with. So we're going to just jump over to this right here. See if we still got it. Actually, you know what? I'm going to link this in Classroom, and you guys should check that out later. That's a pretty cool video. But basically, it goes through what was the point of this most expensive ever project in the world that like a bazillion countries collaborated on. That's this 5 mile ring in a tunnel in Switzerland or France. It's to make scenarios where you have such high energy density. You can think of that as temperature and pressure if you like, that you're going to get exotic particles existing in different combinations than we're used to. I'm talking about quarks instead of in sets of three, being in sets of two or even individually, and also the heavier versions of the quarks than we see today, making some early universe styles of matter. What you can do with this is you can actually have it interact with light and other things too, and you can do some cool modeling on this. So you can basically recreate the situations for matter early on in the universe when pressure and temperature was insane, because you've got an entire universe of stuff exploding outward from a point source. That's really what we're talking about when we say the Big Bang. Now, what's cool about this is as the matter expands outward, it's effectively cooling off. You guys can see that with gas. It's a similar process, even though it's exotic matter. When it expands out to a certain point, it'll start to condense from lone quarks into quark pairs. And then eventually those pairs will fall into trios again, and then you'll finally get your protons and neutrons. When the electrons attach on, then you've got your complete atoms. At the point when you've got a complete atom, all this pent-up energy that kept getting reabsorbed everywhere is finally released in a big flash of light. So you're starting out with lone quarks, going to quark pairs, going to quark trios, and then finally having electrons attached to the atoms, to the protons. By the way, those trios of quarks, 3 at a time, is why the universe started out as almost entirely hydrogen with a smidge of helium. You're really just getting kind of condensation of the quarks down to sets of 3, and a set of 3 quarks makes a proton or a neutron, the very simplest atom, or maybe enough parts to slap together a helium if you get 4 sets of 3 put together in a nucleus. So one thing to know is early composition of the universe, hydrogen, helium. Okay, so it's condensing down. When you get those electrons attached, the universe is no longer opaque, meaning that light can now travel through stuff. It can go right through gas clouds of hydrogen. It couldn't do that before when the electrons were interfering with this. So that's when you get this flash of light. It's called cosmic background radiation. CBR is the abbreviation. You can see this not from just an individual star or an individual galaxy. You can point a radio telescope anywhere in the sky and pick this up. It's basically permeating and surrounding the entire universe, and it's really unique and weird in that sense. So CBR, at first scientists thought it was actually a bug with the radio telescopes, and they weren't publishing their data because like something's wrong with our equipment. We keep getting this one frequency no matter where we point our telescope, and that's weird. And finally, 2 different teams, I think on opposite sides of the globe, both published the results that they were having a hard time fixing this problem. And then they realized that everybody else was having the same problem, and it wasn't a problem at all. It was this bizarre kind of light left over from not long after the Big Bang. It's called CBR. It started out at a really, really high temperature, which matches our experimental results. You guys remember black body radiation? Temperature has to do with frequency, they're correlated. So it started out at a high temperature, but basically cooled off as the universe stretched and expanded and is now down in the radio frequencies. You can also use that as a way to correlate the beginning of the universe and these steps a lot longer after, including that very earliest flash of light. All right. So got the best estimate on age of universe. That number has gotten a lot better since I was in high school as they provide more and more data and they can refine their computer models. There's some weird stuff going on with the universe that we really don't understand well. And we'll talk about that next. The words for we don't know what's going on are dark energy and dark matter. And I think we have time for that. Okay, yeah, let's do that. So we've got early universe, Big Bang goes off. We've got quark soup. No light permeating that. Any light that gets emitted gets immediately reabsorbed. Universe is basically like a solid, expanding, high energy, high temperature disk of quarks individually and in sets of 2. Finally, when hydrogen forms, so quarks in sets of 3 making up protons, and when the electrons reattach, then the universe is finally translucent, and right here you get that flash of light. This disk right here represents the cosmic background radiation that our satellites and European Space Agency satellites have mapped out. Had a cool conversation at a playground too with a dark energy physicist in Davis. Pretty sweet. He's kind of mapping that out and using some cool computer models on it. Anyway, then you got this very spread out hydrogen. It takes a while for gravity to clump it up enough to form stars and for those stars to ignite. So fusion process kicks in, and then you've got the end of the dark ages. This is where the first baby stars start to light up. Some of those things were massive. They blew up in a supernova. The shock wave helped get some other stars going, so you get a pretty cool chain reaction of stuff happening right around here. You're going to get your bigger clumping too in your superclusters and your galaxies. So you're going to have your first proto-galaxies there. And at that point, basically, it's business as usual for like, I don't know, what is 13.7 minus 4.6? I need more coffee. About 9 billion years. One of these stars in here had to have supernovaed to kick out things like nickel and iron, the main ingredients in Earth, as well as all the carbon, oxygen, nitrogen, phosphorus, all the stuff that you're made out of, and also had to have supernova to make some of the heavy elements like uranium and plutonium. And that blast of a supernova spread that material back out, at which point the second time around it clumped up, would have formed our solar system. So our solar system is not original Big Bang material. It has already been processed by a star that had a short and destructive lifespan and blew that material back out. Remember, Big Bang produced mostly hydrogen and helium. The fact that our solar system has all these heavier elements in it tells you it's not one of the original solar systems, it's a secondary solar system. Okay, now that's all pretty simple stuff. Here's the weird stuff. This envelope represents the rate of expansion. This is a cool image to help you kind of grasp that. We've got a fairly steady rate of expansion, but it's inflecting outward. Now, for a while, there was a debate about whether the universe is open, closed, or flat. We don't mean like flat Earth, that ridiculous stuff. We mean, is it expanding at a steady rate? Is it expanding because of the explosion, but slowing down because of gravity? Or is gravity even going to be strong enough with the amount of stuff in there to eventually pull it all back together? Like you guys know, throw the ball up, it comes back down, right? But if you throw the ball really fast, it'll head away from us, but still slow down. But it might be going fast enough to escape the orbit. So it might have escape velocity, but gravity's still trying to slow it down and pull it back the other way, right? What's weird is we're getting an inflection curve outward. So gravity's losing to something else. We don't know what that something else is. Something's causing weird changes in the rate at which the universe is expanding. And our word for the thing that's causing it to expand faster than it should is dark energy. And this means that we don't know what's going on. We know that something's causing the universe's expansion rate to change, but we can't explain that with our existing models yet. And we also know that galaxies are rotating faster than they should be based on just the forces involved of gravity from all the known visible stuff versus the rate of the pull of centripetal force we need to keep it in a stable orbit. So there's a couple other things going on too. You can also see here in this picture, you got what's called gravitational lensing. Light is being curved around some object in the foreground. That's not a visible object, even in radio waves or microwaves or infrared or all. I don't mean visible as in visible light. I mean visible in any electromagnetic spectrum. That's not normal matter of any kind that we know about. And so the thing that's causing extra gravity, our word for we don't know what that is called dark matter. Okay, so if you hear dark matter, it means there's extra gravity. We can tell something's there, but it's not any of the things we know about. And then if you hear the word dark energy, it means we don't know why the inflection on space-time expansion keeps changing. And what's seeming to push things outward at an accelerating rate, despite the fact that gravity is trying to pull things back together. So these are both fancy words for we don't know what's going on, even though we can measure what's happening, we can't explain why it's happening. So that's pretty cool. Maybe we'll figure that out in our lifetime. All right, I think this is a pretty good stopping point. If you guys have time, check out the rest of the PowerPoint. There's some good info in there. I think a lot of that's a lot more self-explanatory than the stuff we've covered so far today. Hopefully this has been interesting. And if I don't see you guys again, have a great summer. Hopefully I'll see you around next year.